Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 11th, 2026, about 5 days ago. It introduces a data synthesis framework that achieves state-of-the-art performance using just 2,000 synthetic samples, representing a 150 times reduction compared to leading methods like MagPi. The paper is titled, "Less is Enough: Synthesizing Diverse Data in Feature Space of LLMs." And as we'll see shortly, the efficiency gains here could really change how we approach post-training data. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates this efficiency frontier directly. In the top scatter plot, the horizontal axis tracks dataset size on a log scale, while the vertical axis shows the win rate. Notice the red points for the author's method in the top left. They reach a win rate of over 20% using only 2,000 samples. Compare that to the blue dot for MagPi on the far right, which requires about 300,000 samples to achieve similar performance. The bottom chart quantifies this gap, showing win rate per 1,000 samples, where the red bar for this method is orders of magnitude higher than the baselines. Figure 2 details the core framework, known as FAC synthesis. The process begins in the top right panel, where the system identifies which internal features are necessary for a task but currently missing from the dataset, labeled as F-miss. This informs the synthesis pipeline shown at the bottom. Here, those specific missing features are inserted into prompt templates, guiding a generator model like Llama 3.1 to produce new samples. The diagram on the left visualizes the goal. By generating data that targets these gaps, the method expands the available data to fully cover the target task distribution. So, having seen the method, Table 1 presents the quantitative results across 4 distinct tasks: toxicity detection, reward modeling, behavior steering, and instruction following. The table compares the author's approach against strong baselines like Alpaca and MagPi. If you look at the row labeled hours near the bottom, it sweeps the board with the highest scores in every category. For instance, in the instruction following column on the far right, the method achieves a win rate of about 21%, which is more than triple the score of MagPi. The final gap row confirms this advantage, highlighting double-digit improvements for nearly every metric. Alright, Figure 3 validates the core hypothesis that feature coverage actually drives these results. In the top scatter plot, the horizontal axis tracks the feature activation coverage score, while the vertical axis measures performance on the toxicity detection task using AUPRC. The dashed trend line reveals a striking correlation, with a Pearson R-value of 0.95, meaning that better feature coverage almost perfectly predicts better model performance. The bottom panel breaks this down further by sorting the methods from left to right based on their coverage scores. As the purple line for coverage rises, the red bars for performance steadily increase, culminating with the author's method on the far right, which achieves both the highest coverage at 82% and the top performance score. Well, seeing the correlation is one thing, but Table 2 gives us a qualitative look at what these internal features actually represent. The first row highlights feature 2039, where the top activated spans all relate to robbery and burglary. Based on this semantic cluster, the system generates the blue synthesized query below it, which explicitly asks about stealing from a neighbor to fill that gap. Moving down, feature 17,612 captures academic dishonesty, grouping phrases about cheating on tests. This confirms that the method targets distinct, meaningful behaviors rather than just random patterns. So, Figure 16 asks if these internal features can transfer across different architectures. The layout is split into 3 panels, representing different generator models: Quinn on the left, Mistral in the middle, and Llama 3.1 on the right. Within each panel, the bars cluster by the source of the extracted features. Interestingly, features from the Llama model, the rightmost group in each section, consistently yield excellent results. Even the powerful QN model, shown by the blue bars, performs well using these transfer features, which proves that the method supports effective cross-model generalization. Wrapping up, the key lesson is that targeting internal feature coverage is far more effective than just adding more text. This method proves we can build high-performing models with tiny, well-curated datasets, potentially shifting the industry toward much smarter, more efficient training pipelines. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.